Let us start. So, Ramon, please.
Thank you very much. Thank you for inviting me to this seminar and present this talk. I shall speak about existence results for B-root subgroups on affine spherical varieties. Here is a brief outline. So, first of all, let me mention that my talk is based on two preprints. The first one is joined with Ivan Arzhantsov, and the second one is joined with Vladimir Zhgun. Let me also mention that the main purpose of my talk is to present results of the second preprint. So the emphasis will be on this one. And also Vladimir Zhgun is attending this talk and requests all the audience to ask interesting questions. So please don't hesitate. So my plan will be as follows. First of all, I would like to discuss some generalities on GA actions and locally nilpotent derivations and root subgroups on maybe arbitrary varieties. The second part will be on root subgroups on toric varieties. And the third part is the main part. So here I'll discuss the main results. And I hope that the audience is very familiar with the first two parts. So the discussion, I hope so. So the discussion of the first two parts will be short, relatively short. So let's see. First of all, let's talk about GA subgroups. We work over a field K, which is assumed to be algebraically closed and of characteristic 0. So the standard notation GA is the additive group of the field. And let's consider an irreducible algebraic variety X. And here is the standard definition of a GA subgroup on X. So if GA X on X, then each and maybe non-trivially X. Then the image of this subgroup in the automorphism group is called the GA subgroup on X. Next. So now assume X is an irreducible affine variety. So we restrict to the affine case. In this case, GA subgroups can be described also in terms of the algebra of regular functions on X, K of X. So in this setting, a key object is a locally nilpotent derivation. So if you have a derivation of this algebra, it is called locally nilpotent. If for every function there is an appropriate power k such that if you apply d to the power k, then f will go to 0. And it is well known. So so now I would like to explain the correspondence between the locally nilpotent derivations and GA subgroups. So given a locally nilpotent derivation d on the algebra, we construct in a natural way an action of GA on the algebra. So this action induces another action of GA on X, and so we get a GA subgroup. And a standard fact is that this map induces actually induces a bijection between the non-zero LNDs regarded up to proportionality and GA subgroups in the automorphism group of X. Now I would like to discuss the general notion of root subgroups. So what is it? Now let's come back to the situation where X is not necessarily affine. Consider a GA subgroup H on X. And suppose we have some other algebraic group F, which acts on X. Let also x of f be the character group of this f. And so the definition says that H is called an f-root subgroup if H is normalized by f. So we have a GA action on X, and we assume additionally that it is normalized by some other group F, which also acts on X. So in this situation, when H is normalized by F, we can consider the induced action of F on the Lie algebra of H. So H is one-dimensional, and so the Lie algebra is also one-dimensional. And the only way for an algebraic group to act on a one-dimensional space is via some character. And so in this case, we get a character of F. And this character is called the weight of H as an F-root subgroup. And now, a very important result of our first preprint is as follows. So suppose we have a connected group F, which acts on X with an open orbit. And now, and suppose in addition that this open orbit is not stable with respect to this H. So so also we have an F-root subgroup, right? And then in this situation, so we have an open F orbit, and it is not H stable. Then there exists only one F stable prime divisor in the complement of this open orbit, which is not H stable. So actually, in this case, this prime divisor is connected with the open F orbit via this action of H. And in this case, for short, we say that H moves D.
Excuse me, Roman. Do
Yes?
you assume that the character is non-zero? The weight of the F-root subgroup is non-zero, or it doesn't matter?
So I thought that it doesn't matter. So my opinion is that it doesn't matter, but maybe.
Okay, thank you.
So maybe okay. Yeah. So if there are problems, and if I find problems, I'll let you know. But I think that in this proposition, there are no restrictions on this character.
Okay. Okay.
Now in the affine case, when we have a bijection between GA subgroups and locally nilpotent derivations, every F-root subgroup on X corresponds to it corresponds to some locally nilpotent derivation, and this locally nilpotent derivation should be automatically also be normalized by B. And moreover, the weight of this LND will be the same. So if you want to try to describe some F-root subgroups on a given affine variety, this is equivalent to describing F normalized locally nilpotent derivation of the algebra of regular functions. Okay, now we proceed to the second part, which is about affine toric varieties. So let's take an algebraic torus T. Let's consider its character lattice. And let's fix the definition of a toric variety. So we have an algebraic variety group with an action of T. And if this X is normal, irreducible, and have an open T orbit, then it is called toric. Let me emphasize that in this definition, I don't require the action to be effective. So for me, it is much more convenient to admit non-trivial kernel for this action. Okay, and the following fact describes, so provides a sort of a classification of affine toric varieties. So up to T equivariant isomorphism, affine toric varieties are in bijection with pairs MG, where M is a sublattice in the character lattice, and G is a finitely generated cone of full dimension in M. So actually not in M, but in the rational vector space spanned by M. And now I actually, so in a minute I'll explain the correspondence explicitly. Now let me mention that instead of this pair MG, one can also consider as an equivalent data the corresponding intersection. So if you take all so-called integer points in this cone G, we get a submonoid in M, and this submonoid is finitely generated and saturated. Saturated means that this monoid, so in general, a saturated submonoid or in a lattice is given by the intersection of some lattice with some cone. And I wanted to say that so the pair MG is actually equivalent to gamma. So we already know how gamma is defined. It's determined by M and G. Maybe I need to say that we should take a finitely generated and saturated gamma. Okay, so given such gamma, we recover M by this formula, just as a lattice spanned by gamma, and we recover the cone as the convex cone spanned by gamma. And now let me describe explicitly the construction of an affine toric variety. So given such a pair M and gamma, we can compute the M and G. We can compute this corresponding monoid gamma. We consider the semigroup algebra of gamma and consider its spectrum. And so this spectrum will be the required affine toric variety. So here is the description of this K of gamma, right? In order to proceed, so our goal in this second part is to describe T root subgroups on affine toric T varieties. And so to do that, we need to introduce some additional notation. We shall need the lattice dual to M. It is defined. It is denoted by N. Also, we shall need the corresponding rational vector space. E will be the cone dual to G, and maybe the most complicated notation is E1. So this maybe I'll try to draw here. Maybe, yeah, comment. So we have our cone E. Maybe. And we consider its rays, one-dimensional faces. So here there are three of them in this picture, and we consider the intersection of each of these rays with the lattice. And in this case, we consider the lattice N, right? And E1 is by definition the set of primitive elements of the lattice lying on these one-dimensional faces. So in this case, there will be three such elements. So we have three rays, and for each of this ray, we get only one such element, primitive element. Here is the definition of the set E1. Okay, Sorry. How to proceed? Yes. Maybe I should erase this. We proceed. Now the notion of Demazure roots. So let's take such an element in E1. Let's call it rho. And for this element, one defines the set R rho of E, which consists of all elements in M, for which the pairing with rho is given is equal to -1, and the pairing with all other elements in E1 is non-negative. So I'll show you a picture on the next slide. So let me complete the definition, and we shall proceed. And we construct these sets for every row in E1, and just take the disjoint union of all the constructed sets. And by definition, this disjoint union will be the set of Demazure roots of the cone E. And here is an example. Here is an example, maybe a two-dimensional example. So in this case, we have so M is just the lattice of rank 2. We consider this cone here, G. It has two faces. It has two faces, and the corresponding elements row 1 and row 2 are these red arrows. And for row 1, the corresponding set of Demazure roots is given by these green points. So we get these green points here. So we have a series of Demazure roots corresponding to row 1. And similarly, we have a series of orange Demazure roots corresponding to row 2. So this is a sort of illustration, a sort of an illustration of the notion of Demazure roots. But perhaps, so I believe most of the audience is aware of this notion. Okay, and let me proceed to the description of root subgroups on affine Toric varieties. So suppose we have an affine Toric variety X given by the data M and G. Now let's take a Demazure root corresponding to an element rho in E1. And so given E, so given this E, we define a locally nilpotent derivation dE on the algebra. And here is an explicit formula for this derivation. So remember that so the functions f lambda form a basis of this algebra, and so it suffices to define the derivation on all elements of the basis. And for a given basis vector, we have this formula here. And an easy check shows that this formula indeed defines a local nilpotent derivation, and it is also T normalized, and thus we get a T root subgroup on X. And here is a theorem. Here is a theorem. So the first two parts they provide a complete description of all T root subgroups on affine Toric varieties. So every T root subgroup on X is uniquely determined by its weight, and the set of weights is just the set of Demazure roots of the corresponding column. So here is so this is a complete description of all T root subgroups on affine Toric varieties. And the third part is a some geometrical property. It says that if you take an arbitrary t-stable prime divisor in X, then it can be moved by an appropriate t-root subgroup. So this is the statement. Why did I color this statement with blue? This is because I'm going to generalize this statement for the more general situation of affine spherical varieties. So please memorize this statement. So for every t-stable prime divisor, there is a t-root subgroups which moves this divisor. So we shall come back to it at the end of this talk. We shall come back to a generalization of this statement to the more general case of affine spherical varieties. Okay, and now I proceed to the third part of my talk. So to the main part, I shall speak about affine spherical varieties. So spherical varieties are generalizations of toric varieties, and let me explain how this generalization goes. So instead of T actions, we consider actions of an arbitrary connected reductive algebraic group, so which is denoted by G. For simplicity, you may assume that G is equal to SLN. It's a very good example. When you deal with connected reductive algebraic groups, it's very common to fix a Borel subgroup and a maximal torus inside it. And so B is a Borel subgroup here, T is a maximal torus, and here are interpretations of these subgroups in the case of SLN. And also, I shall need the unipotent radical of B, which is known as a maximal unipotent subgroup of G. And next, one more important notation will be the set of dominant weights, of our Borel subgroup. So it is well known that the dominant weights are in bijection with finite dimensional irreducible representations of G. Okay, and here is a short remark on what happens in the toric case. In the toric case, G is equal to B and is equal to T. The unipotent radical is trivial, and the set of dominant weights is just the whole character lattice of T. Now I'm ready to define spherical varieties. So here is the definition, which generalizes the definition of toric varieties. So let's consider a G variety X, which means that we have X equipped with an action of G. X is called spherical if it is normal, irreducible, and possesses an open B orbit. This is a definition of a spherical variety. And again, if we restrict this definition to the case of where G is a torus, we get precisely the definition of a toric variety. In our first preprint, it was proposed that a proper generalization of T roots in the toric case is given by B root subgroups on spherical varieties. So in our preprint, it was proposed to study B root subgroups on spherical varieties. And I'm going to discuss B root subgroups on affine spherical varieties during this talk. A global problem, which is open at the moment, is to describe all B root subgroups on a given affine spherical varieties. You remember that in the toric case, maybe in the affine toric case, there is a complete classification, or maybe a complete and simple description of all T root subgroups. And it turns out that in this more general spherical case, to describe all B root subgroups on a given affine spherical varieties is a much more complicated problem. Here is a very useful characterization of affine spherical varieties. So this theorem holds for not only for affine but also for quasi-affine case. So given an irreducible normal quasi-affine G variety X, we have two equivalent conditions. The first one says that X is spherical, and the second one says that the G module. So we can consider the algebra of regular functions. We regard it as a G module. And the condition is that this G module is multiplicity free, which means that every irreducible representation of G occurs in this G module with multiplicity at most 1. And from now on, we assume that X is an affine spherical G variety. So we work only with in the affine case. Here are two important invariants of an affine spherical variety. Actually, this invariance may be defined for an arbitrary spherical variety, not necessarily affine, but I need only the affine case. So the first invariant is the weight lattice. This is the lattice of weights of B semi-invariant functions, maybe B semi-invariant rational functions in X. And this will be always a sublattice of the character lattice of T. So we have this weight lattice. This is a sublattice of the character lattice of T, and it is denoted by M. And the second invariant is the weight monoid, which is defined similarly to M. We consider the weights of all B semi-invariant regular functions in this algebra, QFX. So this is a misprint here, not on but in. And this will be always a submonoid. So gamma is always a submonoid of M. And in the case, moreover, it is finitely generated and saturated. So we actually get, but maybe, yes, an important property, and also one important property is that this gamma generates M as a lattice. And so we get a picture very similar to the picture we've seen in the Toric case, right? So we have a lattice, we have a finitely generated and saturated submonoid in this lattice, and it generates the lattice. Yes, it generates the lattice. Now, for every lambda in the weight lattice, we can fix the corresponding B semi-invariant rational function of weight lambda. It is unique up to proportionality. And without loss of generality, we may always assume that these functions multiply in this way. So the product of f lambda and f mu will be always equal to f lambda plus mu. Now we consider the recall that k of x as a G model is multiplicity free, and all the simple G modules which occur here have their highest weights in gamma, and so we have this decomposition, right? So, and an important remark says that it may happen that this decomposition. So at the very beginning, we regard this decomposition as a G model decomposition. But in some cases, it happens that this decomposition is a gradient. And so in this case, this happens exactly in the horospherical case. Maybe some of you are familiar with this class of varieties. So horospherical varieties form a very important subclass of spherical varieties. And maybe this subclass is the closest one to the toric case. So a general idea is that if you want to generalize some properties from the toric case to the general spherical one, the first thing you should do is to try to generalize to the subclass of horospherical spherical varieties.
This is a definition of horospherical variety.
This can be taken as a definition in the affine case. But of course, it has several other equivalent reformulations. When you take the subalgebra of U invariant regular functions, it can be decomposed like this. So when you consider any given simple G module, then it has only one-dimensional line of U invariant vectors. And this line is spanned exactly by highest weight vectors. In our case, these are F lambdas. And so when you take this subalgebra of U invariants, it decomposes like this. And we already know this construction. So this is actually the semigroup algebra of gamma. And in this way, we get a natural toric variety with the same weight monoid. So this is why we can take the spectrum of this subalgebra of U invariant functions. And this will be naturally a toric variety with respect to the action of T. Moreover, it's obvious that these M and gamma will be the same as in the general construction of toric varieties. Okay, given this inclusion of the U invariance is included into K of X, and we get a natural T equivariant morphism from X to Y. A small remark regarding a possible classification of affine spherical varieties. So again, in the toric case, we perfectly know how to describe all toric varieties. And we know that all such varieties are in bijection with finitely generated and saturated cones in the lattice, in the character lattice of T. In the general affine spherical case, the situation is a bit more complicated. So it is known that given gamma, there are only finitely many affine spherical varieties with this weight monoid. And also there is a complete classification, maybe complete combinatorial description of all such varieties. But the most delicate point here is to describe the algebra structure in each of these cases. And this is an open problem. So we get a sort of classification, but we don't know much about the corresponding algebra structure, which is also important. And so we work with affine spherical varieties on this combinatorial level. If we have established this relation between affine spherical varieties and affine toric varieties with these M and gamma, we shall need all the same notation we introduced before for the toric case. So we consider the MQ, the dual lattice N, the dual rational vector space, both cons G and E, and this subset E1. Okay. Now let's discuss some natural division of B root subgroups. Suppose we have a B root subgroup H on X. Then, since it is B normalized and U is a subgroup of B, which has no characters, this means that H commutes with U, and therefore it preserves the subalgebra of U invariant regular functions. And there are two alternatives here. The first alternative is that H acts trivially on this subalgebra of U invariants. And the second alternative is that is the opposite case, right? When H acts non-trivially on this subalgebra. And the first case, and in the first case, we say that H is vertical, and in the second case, we say that H is horizontal. And here is some explanation of this terminology. So we come back to the morphism from X to Y. This morphism is H equivariant, and the term vertical is explained by the property that in this case the subgroup, the B root subgroup H, preserves the fibers of this morphism, and so by this reason it is called vertical. Okay, and here is a geometrical interpretation of these two notions, vertical and horizontal. So H is vertical if and only if it preserves the open B orbit in our X, and H is horizontal otherwise. But moreover, in the horizontal case, we already know that there is only one, or maybe exactly one, B-stable prime divisor in X, which is moved by H. So remember the general fact I mentioned on the slide on general F-root subgroups. And a small remark that in the toric case, all root subgroups are automatically horizontal. So in the toric case, there are no vertical T root subgroups. So this vertical is a feature of the general spherical case. Let me now mention some constructions, maybe some simplest constructions and some general construction. So the first construction is about central root subgroups in U. So maybe let me draw some picture here. So for example, in SLN, you have the subgroup of you have the Borel subgroup consisting of all upper triangular matrices, and if you consider the subgroup U, which has ones on the diagonal, there is a central root subgroups which corresponds to this corner here in this picture. So the one-dimensional, one-parameter root subgroup corresponding to this box lies in the center of U. Therefore, it commutes with U, and moreover, it is normalized by T. And so we can conclude that this subgroup is automatically normalized by B. And so the action of this one-parameter subgroup induces a very natural example of B root subgroups. So if you have an arbitrary spherical G variety, you can always consider, you can always take such a central root subgroup in U, and it will always give you a B root subgroup on your X. But of course, since this root subgroup is contained in B, it preserves the open B orbit, and therefore it is vertical. So we have for free some non-trivial examples of vertical B root subgroups. Okay. The second construction is also well known. This is the construction of replicas. So if you have a B normalized LNDD on your algebra of regular functions, then you can take f lambda in the kernel of this D, and you just multiply your D by this f lambda, and this will give you another B normalized LND. And you can also compute the weight. Yes, you just the weight is shifted by the weight of f. And let me also mention that in our first preprint with Ivan Arjantsev, we proposed a general construction of horizontal B-root subgroups, which generalizes the construction in the Toric case. But I'm not going to talk about this construction because it will not be needed here. So in my talk, I just mentioned here that we get a general, so we have a general construction. And let me also mention that this construction is especially effective in the spherical case. Okay, a couple of words about the weights of B-root subgroups. The first property says that the weight of every B-root subgroup on X is dominant. So every weight is dominant. This is non-trivial from the definition, but one can prove this. The proof is not difficult. And also, when H is horizontal, then its weight will be necessarily a Demazure root of our con E, which in particular means that the weight of any horizontal B-root subgroup, it should lie in the lattice M. Let me mention that in the vertical case, there is no such property in general. So in general, there may exist vertical B-root subgroups whose weight doesn't belong to M. But in the horizontal case, we always have this property. And actually, this second property is very simple to prove because remember that H is horizontal if it acts non-trivially on the algebra of regular functions or on the algebra of U invariants. But this algebra of U invariants is just the algebra of regular functions on T on the toric variety Y. And so from the description, from the classification in the toric case, we necessarily get that this weight must be a Demazure root. Here are some remarks. So examples show that there may exist several different B-root subgroups of the same weight. So in this general spherical case, it's not true anymore that every B-root subgroup is uniquely determined by its weight. So remember, in the toric case, it was true, but in the general spherical case, this is not true anymore. And in the horizontal case, we can come back to this proposition here and see that given a horizontal B-root subgroup, its weight should belong to lambda plus and also to the set of Demazure roots. It turns out that if you have a weight which is in lambda plus and which is a Demazure root, it's not necessarily true that for this weight there exists a horizontal B-root subgroup. And actually, on the next slide, I shall show an example of the situation. But this property is true in the spherical case. So we proved in the first preprint with Ivan Arjantsev that in the spherical case, if you have a weight which is dominant and is a Demazure root, then there always exists a horizontal B-root subgroup of this weight. And now the example. So here we have X is just the three-dimensional coordinate space. We consider the group SO3 times scalars. Here is the simplest possible action, SO3 times scalars. In this case, the character lattice of T, of the maximal torus, is naturally isomorphic to to the lattice of rank 2, which is drawn here. In this picture, the set of dominant weights will be formed by all weights lying on the right half of this picture. So the weight lattice M consists of all points, of all even points. So the sum of the coordinates is even. And the weight monoid here is generated by the points 1, 1, and 0, 2. So it is drawn with these yellow lines. So here is the weight monoid, and maybe the corresponding cone G. And also the set of Demazure roots. So we have a row of black Demazure roots here, and a row of green Demazure roots of here.
Excuse me, if you take only 2 generators for this weight monoid, it would be not saturated, as far as I.
But it will be, because I consider
you consider the sublattice.
Yes,
okay.
Here is the lattice. I don't consider the whole lattice. I consider a sublattice of index.
Yes, you're right.
In this case, these 2 points indeed generate the corresponding monoid. Okay, and so as I said, there are 2 series of Demazure roots. So the black one and the green one. If you want to consider this intersection here. So if you consider only Demazure roots which are dominant weights, then we must remove the black ones, and so we are left with only with these green ones. But simple computations show that the first Demazure root, which is marked by this red cross, it doesn't occur as a weight of a horizontal B root subgroup, but all other green Demazure roots, they do occur as weights of B root subgroups, horizontal B root subgroups. So this is an example. So this example shows actually that even if you restrict to the set of horizontal B root subgroups, it's not so easy to describe the set of their weights, because there may be some complicated examples like this. Now let's discuss B-stable prime divisors on X. So DB. So let's introduce some notation. DB is the set of B-stable prime divisors of X. So we consider all B-stable prime divisors. Among these, we can choose all G-stable prime divisors. This is a subset. So G is a bigger group than B. Then there is a smaller number of B-stable prime divisors which are G-stable, right? And the complement and the divisors which are B-stable but not G-stable, they are called colors. Color. So this is a standard terminology in the theory of spherical varieties. Okay. And now we have a natural map. So given a color, we can construct an element of the dual lattice N. And here is the formula. So if you want to take the value of your image of D on a given weight lambda, you just take the function f lambda. Recall that f lambda is the unique up to proportionality B semi-invariant rational function of weight lambda, right? And you just take the order of this function along the divisor D. So this is the definition. And one can mention that, so maybe one can notice that in this case, we have explicit expressions for the weight monoid and for the corresponding dual cone. So the weight monoid consists of all weights for which the parent with every divisor is non-negative, and the cone E is just generated by the images of all these divisors. Okay. In order to proceed, I need to say a couple of words about the division of colors next. So actually, in the theory of spherical varieties, all colors of a given spherical varieties can be divided into 3 different types. And now I'm going to describe how this is done. So let's start with the color D. And we choose a minimal parabolic subgroup containing B that moves D. So recall that. So let me explain the notion of a minimal parabolic subgroup. In the case, so let's discuss the case of SLN. So suppose you have SLN. Maybe let's take SL6. And in this case, we know that the Borel subgroup is given by all upper triangular matrices. If you want to obtain a minimal parabolic subgroup containing B, so this is B, you can choose any negative simple root, for instance here. So you add to your matrices some additional box just below the diagonal, and this will give you a minimal parabolic subgroup. And in this way, one obtains, so in this particular case of SL6, so you can see that we can choose 5 such minimal parabolic subgroups. Okay, and now the point is that for every D, for every color D, there exists a minimal parabolic subgroup. Q, such that it moves D. And the reason is very simple. The reason is very simple. So assume the converse. Assume that none of the minimal parabolic subgroups moves D. Then D will be stable with respect to this each of these minimal parabolic subgroups. And the point is that the whole SL6 is generated by all such subgroups, minimal parabolic subgroups. And so if every minimal parabolic subgroup preserves D, then D will be preserved by the whole group G. In this case, it will be G stable. But we consider colors which are not G stable. Therefore, there always exists at least one minimal parabolic subgroup which moves D. So this is the point. Let's come back to our slides. Now, if you consider the quotient of such a parabolic subgroup modular its solvable radical, you will get SL2 or PSL2. And now, if you take a point in the open B orbit and consider its stabilizer in Q, then you can consider the image of this stabilizer in the group K. And it's easy to show that k modulo this kx will be spherical. It will be spherical as a key variety, and so this will give you three possible cases. Cases u, t, and n. And the first case is where kx contains a maximal unipotent subgroup of k. The second case is where kx is a maximal torus, and the third one is where kx is the normalizer of maximal torus of k. So you consider subgroups of SL2 which have positive dimension, and you just classify. So it's not easy to it's not difficult to show that for each positive dimensional subgroup in SL2, exactly one of these possibilities occurs. And so we get these three cases. And corresponding, so given these three cases, we assign the corresponding case to our color D. So remember that we start with D, we do something, and we get one of these three cases. We say that D, in this case, we say that D has one of these three types. And a standard fact in the theory says that this type is well defined. So if you start with a different minimal parabolic subgroup, if you start with a different minimal parabolic subgroup, you will come to the same type, And so now the colors of spherical varieties are naturally divided into three types. And so we shall use them in what follows. And having this classification of colors, or maybe division of colors into three types, we can say something about moving them. We have the following proposition. So which in a fine case it was mentioned in the first preprint, and in the second preprint it was proved by a geometrical argument in the general case, not necessarily a fine, that if you have a color of type U or N, then it cannot be moved by a B root subgroup. So if you take an arbitrary B root subgroup, it doesn't move. It never moves colors of type U and N. And so if you want to move some B-stable prime divisors, you need to consider G-stable prime divisors, all colors of type T. As for colors of type T, there may be situations where such colors are also not moved by B root subgroups. So, but there do exist examples of colors of type T which are moved by B root subgroups, and so the picture is not clear at the moment. And here is a simple example. So if you take G equal to SL2 and consider the homogeneous space SL2 modular the maximal torus, then there are two colors, both are of type T, but it can be easily shown that there are no horizontal B root subgroups on X. And so there exists no B root subgroup which moves any of these two colors of type T. Okay, and now I proceed to results of the second preprint, where we present some sufficient conditions for existence of B root subgroups. And the main ingredient here is the so-called local structure theorem. Before stating this theorem, let me introduce some notation. So what is the construction? What is the construction? So you have your affine spherical variety X. Inside X, you have G-stable prime divisors and colors. And what you do is you remove some colors from X and consider the corresponding open subset. So this is what you do. You remove some colors. And for any subset F of colors, we just take, so we can consider the union of the corresponding colors, and then we remove this union. So we remove all colors in F, and what we get will be denoted by XF. So given any subset of colors, we consider the open subset, which is denoted by XF.
Shouldn't
Right.
this collection be finite?
Yes. The set of B-stable prime divisors is always finite. So all these sets are finite here.
Okay.
Okay, and now, so having removed some colors, you get a smaller subset in X, and you consider its stabilizer. So you consider the largest subgroup of G, which acts on this open set. And this largest subgroup, of course, your subset will be B-stable. It is always B-stable because you remove only B-stable prime divisors. So this subset is B-stable, but you consider the largest subgroup which stabilizes this subset. And so PF will be a parabolic subgroup of G which contains B. So given a subset of colors, we consider an open set of X and consider the corresponding parabolic subgroup of G. So, okay, and now we are ready to state the local structure theory. So, suppose we have such a subset F. We consider the corresponding parabolic subgroup PF. We consider its Levy decomposition. So L will be a Levy subgroup. PU will be the unipotent radical. And the main statement, so the main assertion is that there exists a closed L-stable subvariety Z in your XF, for which the map PU times Z from PU times Z to XF given by a concrete formula, so given by just multiplication. So you get so you have your subset, you have your subvariety Z, and you just multiply it by the elements of the unipotent radical, and you get all your subset XF. Okay, and so this map is actually a P equivalent isomorphism. P equivalent isomorphism. And here I just mentioned the natural formula via which P acts on PU times Z. Okay, so you have your open subset XF, you have the corresponding parabolic subgroup, and you have this local structure theorem, which says that you have a subvariety, closed subvariety Z, for which the action of PU will give you the whole open subset XF. And there is a additional statement which says the following: if your parabolic subgroup is the stabilizer of all the colors, or in other words, PD is nothing but the stabilizer of the open B orbit. So with this additional assumption, the derived subgroup of L acts trivially on Z. So you can see that Z is a priori an L variety, but L is some reductive group. But in this particular situation, it turns out that the semi-simple part of this reductive group acts trivially. And so actually you get just a toric variety. So Z will be a toric variety in this situation. And what I should say here that this condition, P equal to PD, it is of course fulfilled in the case where you take the whole collection of colors as a subset F, right? So if you take F to be the whole set of colors, then you get for free this second property, which is very, very important actually in applications. Okay, and the small addition to this theorem says that if you take a color of type T and remove all colors except for this one, then the second part of the local structure theorem will also hold. So we know that it holds automatically in the case where you remove all the colors, but it turns out that it holds when you remove all colors but one, which is of type T. Okay, so this is the local structure theorem. Now we want to apply this theorem in order to study B root subgroups on X. So suppose we have a B root subgroup on X. You can you can consider the set of colors which are stable with respect to this H. Then H preserves automatically the corresponding open subset, and thereby defines a B normalized locally L and D on the corresponding algebra of regular functions. Right. So if you have a B root subgroup of X on X, you just remove all the colors which are stable with respect to H, and then you get a smaller subset, which is of the form as in the local structure theorem, and you can study this subset. An important note says that this set of colors FH is equal to the whole set of colors when H is vertical or moves a G stable prime divisor. And in the case where H moves a color of type T, then you get all the colors except for this one. Remember that a given B root subgroup can move only one B stable prime divisor. So this case is a priori. It consists of either all the colors or all colors but one of type T.
I'm sorry, do we claim that X sub FH is an affine variety?
No.
But we still consider the algebra, yes?
Yes, but I can. So in general, this subset is quasi-affine, and for this quasi-affine variety, I can consider the corresponding algebra of regular functions.
Okay,
there is no
thank
problem.
you.
And actually, so if you have a B root subgroup on this smaller variety, which is quasi-affine, we still get a local idempotent derivation on the corresponding algebra of regular functions. This is a very important point, and thank you for your question. This is a very good question. Okay, so so here is our situation. When we have a B root subgroup, we can consider an H stable open subset, just as in the local structure theory. Now we study this situation. So now we proceed to study in this situation. Now we consider the set of all colors, or the set of all colors except for one of type T, and we try to study the corresponding local idempotent derivations on the algebra of regular functions on this open subset. So now the problem of describing all B root subgroups on X splits into the following two. So according to our consideration, so describe all B root subgroups on our open subset. And when you've done this, you can then ask which of these actions do actually extend to B root subgroups on the whole X. So this is a natural division of your problem. So if you want to describe all B root subgroups on your affine spherical variety, in this way you can split your problem into the following two ones. So the first one and the second one. And it was surprising for me that in our second preprint we were able to completely solve the first of these problems. So this actually was very surprising. And next time I'm going to discuss or maybe explain or try to explain how we solve this problem. Okay.
So I would like to mention that this gives somehow uniqueness result. Yeah. So.
Yes, of course.
Yeah.
Yes, of course. So, but maybe it's not so easy actually. So every B root subgroup on your whole affine spherical variety, it fits into one of these finitely many open subsets, right? And for each of these open subset, you get a complete description of B root subgroups on this open subset. Is it clear? Okay. Okay. So now I would like to consider the problem of describing B root subgroups on XF. And so here are some repetitions here. So recall that XF is isomorphic to PU times Z as a P variety. We know that Z is a toric T variety, which is very important for us. We can also choose a point in the open T orbit inside Z, but maybe it will be not needed here. So maybe it is superfluous here, but still. In what follows, we shall also need the weight monoid of this toric variety, which is in the general case, it is this toric variety is quasi-affine, but still we can consider its weight monoid. Okay. And in order to formulate the main result, we'll need to look at the algebra of. So actually, let's have a look. So we have this PU times Z, and on this variety. So when you consider only the first component, you can consider the action of L on it. This is the usual action by conjugation, and so we can consider the corresponding action of L on the Lie algebra of PU. So we consider the Lie algebra of PU and consider the adjoint action of L on it. We can decompose it into a direct sum of simple L submodules, or maybe irreducible L invariant subspaces. And it is known, maybe well known, that in this decomposition, all summands are pairwise non-isomorphic as L models. So we get a multiplicity-free representation here for L. And for each of these representations, we can consider its highest weight.
Yeah, I would say that Alexander Grigorievich would be upset here because this was partly known by Weinberg.
Yes, of course.
Yeah.
But I skip all this discussion.
Yeah, sure.
So, let me just mention that this result is actually well known, and it's surprising, or maybe it's sort of ridiculous that it was published only recently. But the result
I would
is
say
well,
it is contained in the survey on Lie groups and Lie algebras of
41,
1988 or 8. I don't remember which year.
41.
I would say that
Much
Koster
earlier than
has
Koster's
more
paper.
precise formulation that was in Lie groups and Lie algebras. So formally, there is something a little bit more in this paper. However, most of them was well known to Ernest Borisovich. I mean, and he was doing this independently. So.
Yeah, you're right. So here I just wanted to cite a source where you can definitely find a proof of it. But the result itself, it was known much earlier. You're right. And now I consider the set of highest weights. And for each highest weight, I fix a non-zero vector in the Lie algebra PU, and consider the corresponding one parameter subgroup in U, one parameter unipotent subgroup, right? And I can consider the action of U alpha on my open cell, or maybe open subset, by the simple formula. You just multiply the first component on the right. So here is the formula. U alpha acts on our open subset just by multiplication on the right of the first component. And it's easy to check that in this way we get a B root subgroup on our open set. And we consider the corresponding B normalized LND and denoted by delta alpha. So this is what we need. So these are some preparations for our main theorem, which will be on the next slide. So here is the theorem. Before I state it, I still need to introduce some notation. So I consider all highest weights with respect to L, which satisfy this property here. So for which the difference with alpha, with mu, belongs to M, and even smaller subset where the difference belongs not to M but to the weight monoid of Z. So here are some just subsets of the set of highest weights of L in PU. And now I'm ready to state the main theorem, solving which gives a complete solution to the first problem. So here is an explicit formula for every for an arbitrary B normalized LND on the algebra PU times Z. So every such LND of weight mu has the following form. You can see that the first part, so C alpha are just constants, phi f mu minus alpha are just functions, and here are the derivations delta alpha introduced on the previous slide, and delta Z is the component on Z. And it comes from a T normalized LND on K of Z, on the algebra of regular functions of Z. And it turns out, so here's the statement. So every B normalized LND of weight mu has this form. And now conversely, every formula of this form defines a B normalized LND on my open subset. And so this gives me a complete description of B root subgroups on these open subsets. And now it's natural to state the following consequence of this theorem, which is a direct consequence. So if you consider all B-normalized LNDs on your K of X with a given weight high, then it turns out that all such LNDs form a finite dimensional vector space. And you can also give a bound for the dimension of this vector space. So, and if there exists a horizontal B-normalized LND of a given weight, then the vertical ones will form a subspace of codimension 1. And the main reason for this is that for all B-normalized LNDs of a given weight, one can choose a common open subset for which they all restrict, which is preserved by all of them. And so we can apply our construction and our result here. And the codimension 1 and the codimension 1 condition here, it follows from this part. So dz, it corresponds. So this is dz, which is responsible to the horizontal horizontal B-normalized LNDs. And this dz, it comes from the toric case. So the dimension of all possible dz's is either 0 or 1 from the toric. So we get this from the toric case.
I'm sorry, could you please remind what is delta alpha?
Delta alpha, this is from the previous slide. So recall, so it is here, delta alpha. We consider the action of the unipotent one parameter subgroup corresponding to alpha on our variety, open subset, given by this formula. As I told, you multiply on the right.
I see.
Now we have this corollary. And let me also mention that the statement itself, it from the very definitions, it is not obvious even that the first part. So it is not obvious that the sum of two B-normalized LNDs of the same weight is locally nilpotent. This is not obvious and non-trivial. Just from the definition, but in this case, it happens that such sum is always locally nilpotent. And now, what we can obtain in the second direction. So now we already have a complete description of all B-normalized LNDs on the open set, and the next natural question is to determine when a B-normalized LND on the open set extends to the whole algebra. Actually, the algebra of regular functions on X will be a subalgebra. In the algebra of regular functions on the open set, right? And so the question is that given a B-normalized LND on the open set, when it preserves the subalgebra K of X. So here is what I said. When we have a B-root subgroup on our open set and consider the corresponding LND, then it extends. So the root subgroup extends to a root subgroup on the whole X, if and only if the corresponding LND preserves the algebra K of X. And here is the main idea of what to do. So if you have generators of K of X, then you what is the problem? You can consider the images. You can apply D to each of these generators. You get some functions Gi, but in general, these functions may lie outside of this algebra. On the geometrical level, this means that these functions may have poles along the divisors, which we removed, right? And how to get the result? So how to obtain a local nilpotent derivation on the whole algebra, on the algebra of regular functions on the whole X? We just need to multiply our L and D by an appropriate function in its kernel. So we want to take an appropriate replica of our D, and so this is the solution of how to obtain locally nilpotent derivations, or maybe B-root subgroups on the whole X, having them only on the open subset. And here is the main theorem on this topic. Here is our main theorem, maybe our second main theorem, which says the following. So if you, for convenience, we can fix any projection operator to the rational vector space spanned by the weight lattice, and our result states that there exists a collection of constants, each constant for a constant for each color, and here is the property. So if we are given some weight mu, any character of T, then when it satisfies a system of linear inequalities, then every B normalized LMD on the open set will extend to a B-root subgroup on the whole X. So this is our second main result.
Yeah,
And
so I want to mention that the color moved by our derivation is not contained in F due to our notations. So these are only colors that are stable. And the second that one can write the proof down that this depends only on these constants can be chosen to depend on homogeneous on the open G orbit. So they are somehow universal. They could be taken universal, not depending of the embedding.
Yes, yes, yeah. You're right. So I would like to comment on this, that for this theorem, one can state various different formulations. So this result can be formulated in different ways. So this is one possible way, but yes, there may be variations, and maybe for I would say that for concrete weights, the set of constants will be maybe improved. So this theorem presents a universal collection of constants, but for some families of weights, these constants may be much better. So this is what I wanted to. This is what I want to say. So here, and this is the reason for variations of this result. And on the next slide, I would like to state some consequences. So actually, this is a technical consequence saying that under some conditions, a G-stable prime divisor or a color of type T can be moved by an appropriate B-root subgroup. The following fact says that the property of this corollary. So here I get the first corollary, which requires some property. Here I state that this property is satisfied by G-stable prime divisors. automatically, so this property is automatically satisfied by all G-stable prime divisors. And the last result, and the last result says that every G-stable prime divisor can be moved by an appropriate B-root subgroup. And remember, so maybe recall that this is a direct generalization of the corresponding result in the toric case. And maybe one more comment that this corollary says that if you consider the action of the whole automorphism group on X, then it of course has an open orbit. But this corollary here says that the codimension of the complement of this orbit is at least has dimension at least 2. Yeah, and maybe that's all. Thank you for your attention.
Thank you very much, Roman, for your well-prepared and very clear talk. Are there any questions, comments?
I have a small question. You have a theorem about the vector space of LNDs on page 25, I guess.
Yeah.
Yes.
Yeah.
This corollary. And if you map this vector space to the tangent space of some point on a variety, what do you get? So is it smaller? Is it an injection?
I think yes. Yes, because actually the main idea of the proof of this theorem, it is based on consideration of the corresponding vector field. So if you have an action of a B root subgroup H, then you automatically get a vectors field on the smooth Lokov. And this vector field will be also be normalized of this weight, right? And any such vector field, so but B has an open orbit on your set, on your subset. This immediately tells you that your vector field is uniquely determined by its value at a single point.
Yes, indeed.
And this is actually how we prove the theorem. And this point, so if you choose this point in a clever way, you can actually get this formula here. And this also so I think that this also answers your question. So if you map to the tangent space, this will give you an injection. Yes.
Yes. Then there is another question: are these LNDs conjugated by B? Sometimes, with some of them maybe. Can it happen?
Conjugated by what?
By B, maybe the corresponding actions. Oh wait, I said something stupid. Okay.
Okay, so as I understood, all these sections are B normalized, right?
Yes, yes.
So
Sure.
B cannot move them.
Got confused.
Okay, no problem.
Okay, so as Roman explained, we have a big open orbit on a affine spherical variety. The complement of this big orbit, I mean the orbit of the automorphism group, contains no divisor. So the next step should be to prove that any affine spherical variety, which is not degenerate, is flexible. So this big open orbit, in fact, coincides with the set of smooth point. But unfortunately, this is still open. Okay.
Yeah, so this is a very interesting question, right? Maybe problem.
Any more questions, comments, suggestions?
I have a question about the same theorem which is on the slide. You describe the B root subgroups in terms of derivations, but can they be described geometrically?
I don't know at the moment, so I didn't think about it.
And what do you mean by geometrically?
I mean, like these special root subgroups acting on the right on the factor PU structure decomposition, something like
Yeah,
this.
but you may write down the exponent. Yeah, so via the how they write.
Formally, you can do it, but this is just, I mean, of course, you can formally write down the exponent, but I mean, something more explicit.
Yeah, this is a good question, and it is related with actually with extending the derivation to the B divisors. Yeah, so just
so far, no such description is available, as I understand. Yeah.
Right, but so you see that you have this this explicit formula for the derivation, and all you need to do is to exponentiate it. I don't know if it is possible to obtain a nice short formula.
Okay.
Okay. More questions?
Maybe a silly question. Is there a simple example of spherical but not toric variety?
It depends on what you mean by toric variety, because when you take a spherical variety, you may ask whether it is toric with respect to the action of some bigger torus, right?
Yeah. I mean that
they
are not
torus,
connected.
Some bigger torus which is not related to G, right?
Yes.
But still, take SL2 quotient by the torus. So this will be two-dimensional, and there is no, it's two-dimensional surface, but there is no two-dimensional torus which acts on this surface. So this is probably the easiest example.
Okay, I see.
Okay, any more questions? If not, then let us thank the speaker again. Roman, it was very nice talk, and we are motivated to study this subject further. Okay, so dear colleagues, see you next time.